uh, 4 speakers from academic institutions, from research institutions, and from private sector. We have 4 speakers, and the first speaker of the second session is Dr. Utain Swangwit. He is Acting Director, Center of Information Technology, National Astronomical Research Institute, Public Organization, or NARIT. His presentation is Utilizing Computer Networks from International Data Transfer, Case Studies from NARIT. Please welcome Dr. Utain.
Okay. Good morning. So, right. Okay. Not everything appear on there, unfortunately. I think some perhaps template issue. Okay. Anyway, so my name is Utain Swangwit. For those who haven't met me before, so I'm currently an acting director of the Center of Information Technology, as well as a chief scientist for the cosmology, high energy astrophysics, computational, and data-intensive astronomy. So I'm double kind of like function as a researcher, as a user, as well as providing these infrastructures and into more operations of things. So the topic that I would like to tell you about today is on the network requirement. I think this is a part that now we're coming up to the point where NARIT and Thai astronomy, not just a consumer of the data from, let's say, other scientific community from outside of Thailand, but now we are start producing much of these data and need to, basically transfer these data out in large quantities and also in a timely manner to be able to satisfy the requirement for the scientific community. So just to give you a brief introduction of what who we are, what NARIT does, what our goal is that is to use astronomy as a challenge, as a goal, and hard questions to basically drive human capacity development and technology capacity of Thailand, and that's what we're doing. So it's not just astronomical research, although the title suggests in such a sense that we also involving a lot of with technology development and so on, and human capacity development. Okay, slow. Okay, so this is our vision and missions. So we aim pretty high to be the world renowned in terms of what we do, in terms of the astronomy, also technology development and innovation. We focus in these kind of like 5 main activities. Of course, the first and foremost is the research in astronomy and also related field, including atmospheric science and space science, and a lot of activity also focusing on technology development and including technology transfer of these knowledge that we have. And there's a huge significant part that we also do astronomical outreach and public engagement in terms of education and so on, and inspiring of the STEM workforce of the future. And the last but not least is also forming and strengthen the collaboration between Thailand and many countries, not just in the field of astronomy, but also in space science and also other areas. Okay, so this is like our infrastructure at a glance. So our first flagship infrastructure is a 2.4 meter telescope. Is the largest optical telescope in Southeast Asia, and also one of the largest in Asia. So this was constructed more than 10 years ago with the first light back in 2012 on top of the internal mountain in Chiang Mai. Our institute is located in Chiang Mai, by the way, so in northern Thailand. So if anyone has a chance, and I would love to invite you to visit us. Apart from the optical telescope, recently we has installed and now in the phase of testing the 40-meter radio telescope. This is primarily to use for astronomical research but as well as joining, participating in the what we call the VLBI network for geodesy, which I will tell you a bit more later on. Apart from that, we also operate numbers of robotic telescope scattered across Thailand. Right now, we have 4 regional observatory, which is some of the pictures you can see here. And then one of the main, what we call also regional observatory called Astro Park in Chiang Mai, where our headquarters and office located. Many of these, all of these places in regional observatory is focused on educations and also research outreach for local university and schools. We also operate a numbers of remote and robotic telescope across the globe, from southern China to Australia to Chile, and also USA, California in USA. And so, yeah, so it's a number of things is happening, and lots of requirement for our facility here. Also, one thing to notice is this under the construction of the 2 13 meters WGOS antenna, which I will tell you in a bit more detail, which is I think much of the focus of today's talk. So yeah, this is the main infrastructure that I just told you about, the National Observatory, both for the optical and the radio. The radio one is located in Hoi Hong Krai National Park in Doi Saget district in Chiang Mai also. Okay, so this is being hailed and seen as a next big leap for us in terms of the requirement to operate such an instrument, the 40-meter class, which is a big deal here in terms of what we need to achieve in terms of engineering and also in terms of instrumentations and science. And this is not just for astronomy, but also rather a great training ground for our engineers as well. And yep, so I think this is again, we will talk a bit more in terms of that. Apart from the 40-meter telescope up in Chiang Mai, I already mentioned the 13-meter WGOS that we'll be using for geodesy network, will already under the construction and installation and should be completed and tested around middle of this year, and that's pretty much the focus on in terms of the network that you know we'll be hearing a bit more. And then another WGOS station that will be in Songkhla province in the southern Thailand, that will kind of extend the baseline in terms of how much of these we can cover in Thailand, as well as acting as a station where we can use, let's say, only use this telescope and operate them in our own Thai VLBI network or the very long baseline network. We also have plans to convert the other kind of like a telecommunication antenna, the 32-meter telescope, one in Chonburi and another in Ubon Ratchathani. So that's in progress and actually applying for funding. And this is some of the simulated images of a well-known source in astronomy, M87 jet, for example, of how much we will be able to resolve and study, for example, using these facilities within Thailand. Okay. Please. Okay. Hang on. Okay. So another major infrastructures in terms of the HPC. So this is the what we call Shalawan cluster, the nickname Shalawan cluster, which we been operating and using since 2005. And been deploying a number of generation. Now we up to generation 3, Spiker. So that's the nickname from Castor, Pollux, and to Spiker. And over the years, so these are the total numbers of CPU cores that we're still using, combining the 3 generations of roughly about 1,600 CPU cores, 12 terabyte memory. There's also GPU, which we deployed 3 to 4 years ago, the V100. 12 of them, and yeah, so interconnection between nodes has been upgraded in the last cluster to 100 gigabit per second from the 56 gigabit InfiniBand. In terms of the storage, we have the Power 5 system called Luster, Right now we're up to 5 petabyte, and as you will see, why we prioritize in terms of storage so much is the amount of data being generated by astronomy. And we also run another virtual infrastructure. This is to serve things like a VDI, a high-performance VDI for engineers and also for scientists who need to do data visualization and so on, and other infrastructure for our engineers. So it's kind of like in development, more like an on-prem cloud kind of thing for DevOps. We are also part of National eSci Consortium, and we are quite proud to basically serve some of the computing time to our partners in Thailand, not just our own researchers. And this is basically a sort of like scientific and engineering need, computing need at Narit, where we have numbers of facilities that we need to serve. I will go over some of these surveys and experiment in a little bit. I already mentioned the 2.4 meter and robotic telescope network. The radio was also main focus. So these are using for things like mission critical for experiment and survey that would need a real-time a turnaround of analysis, for example, and for data intensive analysis. I think there's some that gone off the slide here a bit. Okay, so in terms of using the HPC for research, so it's not just basically, I mean, in terms of astronomy, we're doing anything from cosmology all the way to simulate exoplanets and AGN supermassive black hole. We have a research team doing atmospheric science. And apart from that, the National eSci Consortium, our user also working on things like condensed matter physics, physical mechanics, a number of people doing big data machine learning. We did that ourselves. We are doing that ourselves as well, but also a number of people using that. For astronomy, in terms of using the hypercomputing computings and the requirement, I would say, yeah, so the word from the Big Bang to the big data. So up around year 2000, you see a huge increase in terms of the computing power, and as we call community has captured that in the what's so-called the Millennium Simulation, the first one ever to run the large sort of cosmical simulation from the beginning of the universe all the way to present day, and compare that to the real data. And so at the turn of around year 2000, you start to see comparison, the data observations start to catch up. So on the upper and the left panel here, the wedge here, these are from the real data, one being from the UK Australian collaboration called to the FGIS, the other one from the American side of things. And these are being compared to simulations, for example. These, of course, is what astronomers and cosmologists arrive at the answer or the conclusion that perhaps a lot of the matter in the universe are made up of dark matter, and they are cold dark matter, for example. And now since year 2000 onward, we're in the age of the data deluge. A lot of these experiment that is coming up that will need astronomers and people who provide infrastructures seriously need to consider how we do computing. Sorry. Okay, so in terms of astronomy, we tend to think that this is a proverb, not sure, definitely Thai proverb, but I'm not sure about international. We think of ourselves as being the blind, trying to tell what elephant look like from touching on different part of elephant, right? So as you can imagine, using different only one wavelength or one waveband, you could arrive at different conclusion and perhaps not the correct pictures. And so, yeah, with that in mind, we utilize various other these days we call multi-messenger. So it's not just electromagnetic spectrum going all the way from things like very high energy like gamma ray, X-ray, optical, infrared, microwave to radio, but also now with neutrino particles also being used to observe various of these objects from supernova all the way to supermassive black holes and gravitational wave, for example. So this is a little bit, you know, you probably can say astronomers are a bit greedy when it comes to data and observations. So this is that's why it's kind of like we are victim of our own success in terms of having to deal and planning for these. So this is, for example, at Narit, what we are looking to kind of like prepare for in terms of the data rate in the upcoming 1 to 2 years. So I mentioned I will go into some detail in terms of the project, what we call GoTo, which are now expecting to produce 300 to 500 terabyte per year. There's a number of other experiments called Polar Bear, which is a cosmic background in Chile. this Thai National Radio Telescope that I mentioned earlier. So this will be producing 500 to 700 terabyte per year. There's a neutrino observatory in southern China will produce something like 200 terabyte per year, and the CTA Cherenkov telescope array, as you can see here, this is still under constructions, but once it is up, you expect is to produce something like 1 gigabyte per second per event that has happened. And of course, in terms of the upcoming futures and scary future, I would say, for astronomy is the SKA, or the Square Kilometer Array. Right now scheduled to be 2 parts, one in South Africa, one in Western Australia, with these huge coverage for the antenna over so-called square kilometer. We will expect to produce lots and lots of data, and we expect to basically every day exabyte of data every day. So that will be like around twice of the internet traffic now daily. So that's a scary thought, and I think that is probably one of the key things that we astronomers are looking back and having to maybe learn from, let's say, CERN, GRID, for example, and that's probably most likely what we're going to be doing, like in terms of regional node. That serve data to various different computing centers, and Narit and Thailand would be part of that. Okay. Right. So now to go into some of the use cases. Here is the gravitational wave follow-up. So kind of like a searching for gravitational wave using telescope networks in various wave band in electromagnetic wave. So this is a project that a lot of our astronomers have been involved. So he's one of the PI, Gantana Gon here at Narit. So the projects that is utilize the huge network of optical telescope called GO2. I will go into some detail of that. And there's also a number of optical telescope called network called Grandma, and then also the space satellite called Swarm. So again, we utilize much of these robotic telescopes and Thai telescope, including the radio that will be waiting for this alert and carrying out real-time and quick response to this observation, because you don't know exactly what type of objects these are and whether they're going to have any electromagnetic wave counterpart and how long it will last. So this will have to be very quick and also automated. So this is another part of the program that we are involving with on the Swarm, the satellite that is scheduled to launch soon in June 24 this year. And we are part of the network of the Global Wave Station. For us, it's located in Songkhla Regional Observatory in order to act as a relay node. And for serving such a contribution, we get a guaranteed time on the telescope that will serve us. So now on to the main topics on the GO2, or the gravitational wave optical transient observer. This is a huge beast, basically. So we have 2 sides, one in the northern hemisphere, one in the southern hemisphere. The northern one is in Spain, La Palma on Canary Island, and southern side is in Siding Spring, Australia. So as you can see here, we have basically 4 mounts of the telescope. Each mount has a number of 8 telescopes on that, which will be executed automatically as the candidate or the alert of the gravitational wave comes in, and in the coordinated manner. So it means that it's try to cover the patch of skies. So this is typically, for example, when a gravitational wave is detected, the area where, let's say, uncertainty area that we need to cover as soon as quick as possible is a big area. So as a comparison, that's the size of the full moon on the sky, okay, which is about 0.2 square degrees. And this is the GO2. This is one of the mount, for example, 8 telescope. One of these is a 49 megapixel camera. So in total, there are 4 of these that will be coordinated to cover as much of this sky as quick as possible. And then there's a number of other kind of like size and field of view of other astronomical telescope here. So it's a big effort. This is a network of collaboration from various universities in the UK, in Australia, Thailand, I think Sweden as well, and Spain. So yeah, so it's a huge effort that we've been involving with for a number of years. The data that produced is huge in the sense that even our own like grad students and researchers and astronomers wouldn't be able to do everything and look at every data, eyeball every data. Of course, we will need to use AI and machine learning for that. But of course, training set will have to come from people looking at the data. So this is how we can utilize the public to do the citizen science. So there's a website called Kilonova Seekers, which is the citizen science where the data could, come out fresh from telescope and then shipped directly onto the website, and the public can get on that and help astronomers to help eyeball and classify, and we then use those to train AI and machine learning, for example, to give us even better accurate result and more data bandwidth, for example. And this is what roughly the sort of the data size that we will be having to deal with. So this is kind of like trickle down what sort of number of files and size of file, for example. Number of the telescope, 4 mount, 8 each, so that's 32 telescopes multiplied by roughly about, so this is everything, raw data, calibrated, and some intermediate products, about 240 gigabyte per night. That would be roughly something like 7.6 terabyte. And having the site, one in Spain, Northern Hemisphere, and one in Australia. Thailand is a pretty good place to act as the central repo and also as a mirror site here. So we've been experimenting and doing real-time data transfer as the telescope take the data. We managed to push it through to something like 400 to 500 megabit per second. So to give you a bit of a background, we are now connecting to, inside Thailand, we connect to 10 gigabit per second Uninet. So that's what we have been using for like a year now. And I think the thing is, connecting within Thailand to 10 gigabit is very good. Going outside is dropped somewhat, right, to 1 gigabit, which I think will be the main point later that will tell you that we need more. So basically, what I'll try to tell you here, we need more. So this is kind of like a flow chart of like our pipeline, for example, the two sides, and as the data came in, there's a local computer that basically will processing the data on site and then start pushing, and then of course looking at any interesting event that could occur as fast as possible. And of course, if we find something that would be interesting for astronomers, that will be sent out to as an alert to astronomers to follow up with larger telescope, for example, as quick as possible in terms of, let's say, imaging as well as spectral follow-up. So this, for example, this is one of the example of the observation that was done, and this is a reference image. So I mean, looking by eye, you wouldn't be able to tell anything, but once you use this to take a reference, or to take a difference between the two, we discover a supernova here. This will happen in 2019, for example. Okay, so on to the second point in terms of the VLBI. I think the part that I'll be talking about is in terms of the eVLBI. So is the very long baseline interferometry. So what is interferometry? You see already that there's a number of those very large telescope, especially the radio telescope, that can basically coordinated to execute observation at the same time and to combine their accuracy in terms of the positions and time. So many of these will has to be equipped with its own atomic clock to be able to go down to femtosecond, for example, accuracy, and to be able to correlate the signal back and learn about various different properties, for example, their location on Earth, and how the delay signal that arrive at each antenna, for example, will tell us a great deal about what we want. So this is a usual resolution that you can get. For example, you want to look at something very resolve something very small. You all, I think, heard of the astronomer observing the supermassive black hole, or rather the shadow of it. And this is one of the main technique. One of the technique, actually, not the main. One of the technique that we have to use, because when you look at something very far away, you concern pretty much about the angular resolution. So typically, from optical scopes such as Hubble Space Telescope, where it's not limited by atmospheric dispersion, you get something like a resolution of what we call, arc second. So that's tell you how much you can see things or resolve certain small structures. So with this is optical, so it's quite limited. What we want to do here is normally go into like milli arc second. So this is like 50
milli-arc second if you like, or go into even micro-arc second to be able to see some of these features. So of course, 2 parameters here at play. Okay, so you can increase the diameter of your antenna, for example, to be able to get a bigger, a better resolution, or you can basically reduce your wavelengths or go to higher frequency. And that's what we can do, for example, with the radio telescope, usually go into sub-millimeters or in microwave. So what you need to then is each individual telescope will be observed and amplify and utilize their own signal. And then you have to send these signals or send this data to a center that we call correlation center or correlator, to basically work out all those phase shift and then finally get out those image that you want. So the data that you usually produce from here is quite high. And in the past, people just basically sending a disk. It's faster to send this around, and that's pose a major problem in terms of the waiting time and number of disks and cost and so on. And recently, I think, well, not that recent, but rather from like early, just before 2010, people start looking into what we call the eVLBI. So instead of shipping the disk, people start transfer the data, and then some network in Europe can also even do the real-time VLBI. It means that the data sent to correlation center straight away, and you get pretty much a quick result from that. So this is the kind of things, for example, that what the VLBI in radio can do. So this is, for example, the kind of merging galaxies you can see in optical, using things like Hubble or James Webb, you can get some image like that. But in order to resolve some of these structures, look beyond dust obscuration and so on, you need things like a sub-millimeter wave, and this is image construct from ALMA. So it's a huge array of radio telescope there in sub-millimeters. But this is all good. It tends to be like network of telescope that cluster together in one site. So basically, you might need fiber optics connecting 5 to 10 kilometers of telescope, for example. But in terms of the very long baseline interferometry, now we start talking about sharing and correlating the data from antenna or from telescope all across the globe. So we're talking about thousands of kilometers apart of data, but you can basically get even better, right? As you can see, angular resolution earlier, the effective angular resolution you can get, or aperture, is the distance between your telescope. Okay, so this is a good case that you all heard. Definitely on the Event Horizon Telescope, so you can see the location of these various different telescopes. So basically, you're using a kind of like a Earth-sized telescope here to study this M87 black hole, and you can see the improvement. Actually, well, rather, this is the model as the year progressed, as they collecting the data, and as well as adding more and more stations into the network until, yeah, the result came out in 2017. So that was a pretty good achievement for all. And apart from that, you have various network of VLBI that kind of like localized. For example, here you have East Asia VLBI network, which basically made up of station in China, in Japan, and Korea that kind of coordinate the observation times and so on, and having a similar kind of detectors to observe and then send to correlation center. Oh, this is all a bit jumbled up. Sorry about that. So in terms of next, what we are trying to do is many of these is very important for Earth observation as well. Well, not as in observe the Earth directly, but rather to use these very precise positions that we can measure, and with the telescope located on different continents and different plate tectonics, we can use this to pretty much looking or monitoring at how these plate tectonic are moving relative to one another. So in the area of the global positioning observing system, WGOS is also very useful and very crucial to for us. Okay, so this is the a kind of organization that basically coordinating the observations of the geodesy and astrometry, called the IVS. So these are a number of various stations across the globe. So basically, you have many of these execute in sequence and send the data to their correlation center. Thailand, we are proposing the 2 stations. As you can see here, around this kind of like latitude, we don't have that many telescopes. And yeah, Thailand will be definitely contributing these 2 stations in the region. And so, okay, so this is example of their live stations. Actually, I captured this on Sunday. So this is a station that telescope from Japan and Onsala, Sweden, execute the observation at the same time on one of these stations, and you can see the number of sources that they're observing. This session, for example, lasts only 1 hour, but usually the session that they schedule can last for like 24 hours. And these depend on which network or which group that you participate in. You can expect to do this like a few times a month. Okay, so that will dictate in terms of how much data transfer rate we need in order to be basically don't have a backlog of the data that hasn't already transferred. So yeah, our closest correlator that we'll be working with is in China. So that's in Shanghai, the Shanghai Astronomical Observatory, or SHAO for short. Okay, so this is the kind of the requirement in terms of the recording rate and data transfer that would need for e-transfer. So we're talking, so this is depend on the technology and also the receiver. We're talking about from like 8 gigabit per second all the way up to 32 gigabit per second, depend on the receivers and also the technology of the this recording. In terms of data transfer, of course, now we're switching to e-transfer, but again, some disks still need to be shipped when required, okay, sometime. So this is kind of like the network requirement for transportations. So if you look at the site, we're talking about having to use network of 1 to 10 gigabit per second. But if your correlation center, you would require even more to capture all those data and to be basically able to turn all those analysis out in time. So this is the test that we carry out in the last few months with China, with SHAO. So this is one of our concern that our VGOS will be start operation in a few months, and whether we will be able to join and participate in these how many times a year. So this is a network within China and then connect to the outside world. For example, the CST net in Beijing connect to Jive network in Europe with 10 gigabit network, and to Hong Kong with 10 gigabit network. I think there's a number of countries that connect through Hong Kong and Beijing and so on. And this is within China, us connecting to CST net from Uninet. But of course, before get to that, we have a hub in Singapore. Okay, so in theory, we have like 1 gigabit per second from Uninet. So yeah, so that's our main challenge that we try to test if we can do that. So the aim of this is to basically test, check that if we can, what sort of, so we do this in 3 steps. First, of course, just to look at a route that is go, whether you can do or improve anything, and whether both sides in terms of the transfer speed, whether that is balanced or how unbalanced it is. And then finally, we do this with the real eVLBI software that use the UDT network protocol, and see if we can do that. So yes, I think these are kind of like some of the summaries of the tests that we've done over the last few months with SHAO. At first, looking at routes and so on, and yeah, I think at first, I think we noticed that on our side, although from SHAO, the SHAO come from Hong Kong, and then we attach Cat Telecom and come to us directly through Uninet. But on the way out, we need to have one hub in Singapore before get to that. Okay, and then we also have another network that we connect to the outside world, where the Cat Telecom, of course, now is NT. So we did that test as well. So now we kind of like get a bit more or less kind of like similar or balance between the two. And the first thing that we do then is to do a TCP and UDP measurement using iPerf2, which is a very standard one, looking at how balanced or imbalanced it is, right, between SHAO pushing data to us. But of course, the real requirement is that for us to push the data to SHAO with the data that we need to get to the correlator. So as you can see here, just to go over this quickly is that the imbalance between the two ways is quite stark. So usually us as a consumer of the data from outside world, no wonder, I mean, the network probably prioritize to pooling the data or downloading the data rather than pushing the data outside. So yeah, at first we see some of these numbers, we are a bit worried that okay, yeah, I should conclude that very soon. We worry about that, but next, I think we then test with the real software, with the real tool that we will be using, the Jive5AB, which is utilizing the kind of like a modified UDP protocol. Testing this with both network, we managed to get the real data transfer up to something like 400 megabit per second without much package drop. So this is quite an improvement. I think we kind of like a bit more optimistic about that, and I think further tests will be needed. This is still preliminary, and then hopefully we'll be working with Uninet and also Cat Telecom in terms of improving this ability to push data out to closer to 1 gigabit per second. And this is a kind of estimation of what the data volumes and internal transfer time that we will require for some of these data size, which right now estimate to 5 to 7 days, which is maybe just about enough for doing observations like once every week. So yep. So I think this is looking not too bad. I think we can do better. So I think what we try to achieve next is, of course, with more frequent WeGOS observation, we can do more time resolve observation of Earth system and so on. So this is very important. So I think what we try to propose and push ahead with the communities and Uninet is that I think also in terms of high energy physics, I think we heard from them that they are now requiring even higher bandwidth network. So yeah, I think final goals that I will leave here for you is I think we would require larger than 1 gigabit per second in the near future. Okay, thank you very much.
Thank you very much, Dr. Utain. Any question? Okay. Yeah, please. ข้างหลังก็ได้ข้างหลัง
Thanks for your interesting talk. I am the person from Korea. We also provided the connection for the Korean PABI station, and we heard about your activity from via the Korea Astronomy Research Institute. In Korea, we tell us just one framework is just study to the collaboration between network and astronomy stations and the supercomputer, because so many data was produced, and nationally maybe you heard about is Astronomy Institute. They don't have enough storage for to archive the big data, so they need help from the supercomputing side.
Yeah. So you're talking about CASI? Right?
Yeah, CASI.
Yeah.
So, in your organization, is there any activity between the collaboration between supercomputers and your organizations and others to store it? And that's the one thing is in Korea they developed the software correlate that using the GPU. So and they needed too many GPU resources to do that. They also needed some help from our supercomputer. Is there any
I think definitely in terms of the software correlator, we've been thinking about that and also under development, because as you can see in the not so far future, we will start to have our own Thailand VLBI network. So we have to start doing the correlation of these data ourselves instead of sending to either to Shanghai or to South Korea, for example. With the East Asia VLBI network that I showed you earlier, South Korea at KASI is the main node, is the correlation center there. And I know that, for example, with ALMA, the correlation was done by the GPU, the software correlator that provided by KASI. So yeah, so this is the area where we definitely are looking into, and in terms of storage wise, I think what we have 5 petabyte is still very small, so compared to what our astronomer needs. So that's the area where we really need to kind of like push ahead and definitely collaborating. We have a number of collaboration with KASI in the past, and pretty much I think still active on that. Yeah.
Hi, thank you, Dr. Uten. It's very impressive and very fascinating result that you're showing here. Following the same line of questions, well, I can see you said yourself, you want more, and you have addressed the term of data needs and also the network bandwidth needs. Now, just to fill in the gaps, how about the HPC processing capacity needs? How much more that you think you want to do? And maybe I just extend that into, well, you say you want more. Let's just say, how much more do you see that you need to proceed with the 5 and 10 years plan for all data storage, network, and HPCs?
Yeah, for HPC, this is an interesting case, right? Because when you have like you have 5 petabyte of data, you would expect to have petaflops of computing powers and so on. We will definitely need more. We have to look at this carefully because again, with the data storage, this the amount this high, and we have the for example, supercomputing center here in Thailand, and how do we actually utilize that? I think right now in terms of astronomical computing need, like simulations, that can be easily accommodated by, for example, Lanta, right? We have the team that basically applying for time and using that. Now, when it comes to data, where you have to shift a lot of these, and whether the question is then whether the computing center would be able to accommodate us, that would be one thing, right? And definitely ourselves in terms of resources for computing will definitely need more.
And just a follow-up question, if you can. What would the view narrate on this infrastructure? Would it be sourcing out into the cloud base, or you think you still require the on-premises?
We still think we definitely require the on-premise. Yeah, we still need the on-prem. Data need to be quite close to, to the computing part. Yeah, so we're still looking into that. These things are not cheap, right? So at first I think we prioritize for the storage, and that's what all the value, the investment in infrastructure at the end of the day. But then having data sitting idly in the storage, that's not how we do it. So we still need computing power. Yeah.
Well, thank you very much.
Yep.
Okay, thank you very much. Because we are behind schedule, so thank you very much for your presentation. Okay, before we move on to the next speaker, let me share with you some information about how to check in. Please kindly go to shred.com, SCHED.com. I suppose you received an email from Shred, not Shred, Sked.com, maybe last night. So please go to Sked.com and log in into your account and check into this session. Okay, I appreciate for your cooperation. Thank you very much. All right, we move on to the next speaker, Assistant Professor Dr. Porn Panjonghan. She's from Faculty of Engineering, King Mongkut University of Technology, Thonburi. Her presentation is CERN Alice ITS analyzing log data using AI. Okay, please welcome Dr.
Thank
Porn.
you very much. Okay, good morning. Okay, so the topic that I would like to talk today is a practical application of big data that called AI-based logging system for at least O-square facilities. Okay, I am the team leader that come from the King Mongkut University of Technology, Thonburi, or KMUTT, who work with CERN, or the European Organization of Nuclear Research. Okay, so could you start? Yeah, this project was supported by the NSTDA. This is a National Science and Technology Development Agency, and also CERN and KMUTT. Okay, so here, let me give you a brief introduction about CERN. Okay, so CERN is the European Organization for Nuclear Research that focusing on particle physics. Okay, so they have like 4 detector as shown in here below in this picture. So they do about the Large Hadron Collider. So ALICE is one of the detector that they run the experiment about the LHC. Okay, and they have the ALICE O² system, that is the computing system that will collecting the data and process the data and produce experiment results. And also, actually, we work with ALICE O² team like since like 2013, and right now we work with them like for a long time with several projects. And this project, AI-based logging system, it was started from 2018. Why do we need to have the AI-based logging system? It's come with that like in the past, or the experiment data, it will be handled by human manually, and that is a shifter. They call it as the shifter. So the shifter will handle all the experiment data in the control room, as you see in this figure, and they manage or they collect data, and they also maintain about the systems. So when it has something get wrong, so they need to go through the logs line by line in order to find what is the problem. So that is very hard and time consuming. So here, what we need to do, so we try to make the system that like can collect the data, the log files data, and also we try to handle those data and try to process the data in order to provide the useful information for the shifter as a co-pilot automatically, so that the shifter will easily know what happened in the system and what get wrong and what they need to do with the system. So this is about our work that we try to do. Okay, so here is some example of the log files that you see. It's hard to read and hard to understand. So what we try to do, we try to turn these log messages into the useful information as a dashboard that is easy for the shifter to use with when they want to maintain the system. Okay, so this is a system overview of the ALICE O² online and offline facilities that they have. Actually, they have like 2 main cluster. So the first cluster is the FLP, and the second one is the EPN. For the FLP, it stands for first layer processing. So this part, it will be responsible to get the data from the detector, and then they will transfer this data to the EPN node. And EPN node is kind of like the processing nodes that will run the many experiments that come from the physicists, okay, in order to produce some experiment results. And here they have about 200 nodes of FLP, and they have about 1,500 nodes of EPN. And right now we focus on the FLP cluster first, because this one is very important, because the throughput that they have right now that they said in the document is about 3.5 terabyte per second of the throughput. So it means that like if some of the nodes gets down, so it means that it will have a huge amount of data that will be disappear. Okay, so we focus on the FLP part first. So for each FLP nodes, they will have like the log file from the system, operating system, or from the service that they use, like a database or monitoring tools. And also they have the log file from the application that they have, because they need to read out from the detector. So that will be the application that they use. And so all the log file, we need to collect all of them in our AI-based logging system. So in our AI-based logging system, actually we have like 5 main parts, and I will give you the more detail in the next slide. Okay, so here is our team. So we have Vasco here. He is the leader of FLP cluster. So he from CERN. He act as a product owner here to give us the requirement of the system. And also we have 8 researchers here and graduate student, about like 9 graduate students. And we have like 7 undergraduate students who involved in this project. Okay, so for the first part here, it is about beat. Actually, we use the ELK stack, that stands for Elasticsearch, Logstash, and Kibana as our logging system here. So we use Beat here as a log shipper in order to collect the log files from each FLP node. And it will transfer to the Logstash here. So the Logstash is kind of like the pre-processing node. So it will pre-process the log data because like the log file is kind of like the unstructured data, right? So we try to filter out unnecessary information from the log messages. And we also have the log parser here in order to make the log file to the structured data. So we try to find the template for each log messages. And also we try to retrieve the parameters of the log messages as well. And also we have the Elasticsearch here as the storage. Okay, it come up with the indexing and searching function. And also we do have the data analytic nodes here. This one, it will run the machine learning models like anomaly detection, survival analysis, or root cause analysis, something like that. That's going to be the model that we run in this node. And finally, we have Kibana here. This is the node that we use as a visualization that show as the dashboard. Okay. And the other part that we have, that is a resource estimation. So we do this part because we need to estimate the resource that we need to use in this AI-based logging system in both like computing and network resource, but just for the collecting part, but not just for the machine learning part. So we will show you later about the information that how many resources we use and how much time did we spend with the limited resource. Okay. So this is an example of the workflow for the anomaly detection. So actually this one is for one task of the AI-based logging system. Actually, we have like survival analysis to estimate how much time that the system gonna have left before it goes down, something like that. And for anomaly detection, we try to detect the anomaly in the system. And here, we have this is the log messages, right? And it go to the our AI-based logging system by the log shipper. That is the Beat that we use, and then it will go to the Logstash in order to pre-process the log and to retrieve the parameters and the log templates. Sorry, in order to retrieve the parameter and the log templates, we use the log parser here that we develop and by using Drain. And also we have the Elasticsearch to collect the log templates that we have. And then this part here that you see in the below part, this one, it will happen in the data analytic nodes. Okay, so after the pass log, we will try to group the log again with the process ID in order to see what happened for each process. Okay, and this part, we do it to pre-process the data before we feed those data to the machine learning model. So this part, we will try to do the session windowing in order to, because the log will come as a sequence, right? So it will like, we need to window it in order to give the fixed range for as an input for the CNN model here. And we also do the label here, and it's very hard because like to label which part is abnormal and which part is normal. Right now we have like some guideline from CERN to use as a labeling here. And after we're done with the pre-process the data and it will be ready for the machine learning model here, we use CNN first at this time, but we plan to extend to the other models as well in order to improve the performance of the model. For CNN, that is a convolutional neural network here. And then we predict the anomaly and then we show it in the output on the Kibana nodes here. Okay, sorry that I did not go to here. Okay, so for the logs here, they have different kinds of the logs. We have like system logs, like from the operating system, from the virtual machine as well. They focus about like event like a soft lookup and also about the out of memory. But for the database logs, they have like a MySQL and ProgessSQL, and also for the monitoring tools, the log form monitoring tools, they use the Grafana and InfluxDB right now that they are focusing on. And for the application logs here, this is very interesting because this is the application that is developed by the physicists in CERN. So they collect all the logs that from the application in here, InfoLogger. And for this anomaly detection, we first focus on this part. That is about the InfoLogger data. So for the InfoLogger data, that is just only the application logs, not including the system and service logs here. And this one is very complex because each physicist, they will have their own style to writing the code. So the logs that they produce is come from these physicists. So it will be different styles actually. And here, the amount that they produce for 1 day is about 1.6 million log messages. And also the size of the log is about 4 gigabytes per day, or it is about approximately 1.5 terabyte per year that it will produce from this log file, just only for the InfoLogger. Okay, but you need to think about that when we extend to system logs and service log, it will be more and more than this. And also for our experiment that you're gonna see after this, it comes from an example set of data that is just only 4 days run of the experiment. And this, it produced about 16 gigabytes of data for the log messages. Okay, and the analytical nodes that we use right now, this is a VM. Okay, the resource is about 16 core of CPU and 64 gigabyte of RAM, and also for the GPU, it is a 32 gigabyte of DRAM. Okay, and with this resource, we need to spend about like 2 days for one run. Okay, so if we want to improve our model, so we're supposed to need more resource for this. I want to show you about how complex of the data that we have when we compare with other baseline of the data set. Here we compare with the HDFS. This is the baseline of the data set that people usually use it to compare with. Okay, so for the HDFS, that is come from Hadoop system, that is the log files, and they use it to do the anomaly detection task. So we try to do the anomaly detection here, so that's why we compare with it with the HDFS. For the black color here, that is logs from InfoLogger, that is from CERN application. For the orange color here is come from the HDFS. And you can see that how much is complex when we compare with the other logs. Okay, and here the size of the log that we have is about 5 times larger than the HDFS that we have. And also the number of templates here, since the logs messages, it's developed by the physicists, right? For each one, they will have different style when they're writing the code. So they will have variety of the templates that we have here. It have about like 7 times like more like number of templates more than the HDFS. And also for one sequence, the maximum number of logs per sequence can come up to like 2 million logs per sequence. And here is about the number of the session that we have for both normal and anomaly. So you can see that this one is kind of imbalanced, like between normal and abnormal, because we have very small amount of the anomaly event that we have here. So it have about like 0.48% when we compare for the overall session that we have that marked as the abnormal here. So this one is pretty hard when we want to create the model that can capture the anomaly in the overall session that we have. Okay, so here how we define the anomaly here, I would like to show you that, like, okay, here is the example of the log that we have. Okay, so this is the number of the log templates that we told you that I already tell you that, like, when we have the log message, so we try to use the log parser to get this number. That is the log template. Okay, and then that is like a sequence of the log templates that we have, and we try to create the window here in order to make the fixed length of the input to in order to feed it into the machine learning model. Okay, so the size of the windows here is equal to 10. So it means that for one window, they will have like 10 log messages. And we gonna mark this window as the error when, or the anomaly when we find that they have like a error or fatal in this log, okay, in this message. So how this one come from? It come from that the CERN that will have the guideline that which the template that it will like mark as an error or fatal. So this one we use it to label our input here. Okay, so this is the preliminary results that we have here. We try to do the hyperparameter tuning for the CNN model by vary the window size, the hidden size, and the embedding dimension, and also the kernel size here. And we measure it with three parameters. That is precision, recall, and F1 score. For here, as you see, we try to give more weight to the recall, because this one will reflect about the misdetection, because we do the anomaly detection. So we don't want to that any failure happen or any anomaly happen and we cannot detect it. Okay, so that's why you see that the recall here is kind of higher than the other value. And the overall for the F1 score, right now we can achieve about 80% for the F1 score. But as I told you, this one comes from the data that we have the example set for 4 days run. So if you want to use it like as a generalized for the system, so we probably need to use more data to train the model. And right now, what we spend for one run is it takes about 2 days. Okay, so it's kind of hard. Okay, so we probably need more resource. And also, if we want to improve the performance of the system, right now we focus more about like not just only increase the data set that we have, the amount of the data set that we have, but also we thinking about the explainable graph neural network. That is the model that we're gonna help us to understand more about what happened or what is the root cause of the failure that they have in the log messages. And also we're thinking about the LLM or large language model to use in here in order to like understand about the language that they use, because the log messages come from human, right? Come from the physicists. So that's why we try to apply this method. And also not just only the anomaly detection that we're gonna do, we want to do about the survival analysis and the root cause analysis as well. So that's why it's gonna be a lot of work that we need to do. And for sure that we need, when we have more complex models, so we require more computing resources, like more CPU, more RAM, and also more GPU. Okay, so in conclusion, so this is about like AI-based logging system that is the system that try to collect the log messages in the FLP nodes of the LSO Square facilities, and also we try to analyze the log and try to represent the log as a useful information and easy to understand for the shifter or for the operator of the CERN in the LSO Square. And also currently the system can provide about 80% of the F1 score. And we want to improve this number and try to make it more generalized. Okay. And anyway, right now, we try to achieve higher the performance of the model. So we require more resources in order to train the models and also to produce the results that we want to get. Thank you very much. And yes.
Hello, thank you for the presentation. I have two questions. First one, why do you selected the CNN algorithms? Do you have any performance comparison with other algorithms? First question.
Yes. We ever like try with the LSTM as well, because we thought that is the sequence data, so it should be good with the long short-term memory or LSTM model. But at the end, we find that like for the preliminary results, CNN can perform better the LSTM. Actually, we have one of the publication to publish about this result as well in a conference. Yeah.
Okay, and for the 4 days data, how many anomalies events happened?
Okay.
Are they real or simulated?
It's real. It's come from the actually like they have the test run when before the that at least gonna like they have the test run, so they run as a real event that they have as a real experiment on in the detector, and then they collect those data, and the data that they have they collect from the real test run. Yeah.
And how many times?
How many times? Actually, I cannot remember exactly the number of events, but it has just only 0.48% of the overall. So it means that like it have like less than 10 times.
Then
when they
if
have
it is
the
so
run.
small, then you may need to take care of the imbalanced data set.
Yes, that's right. We need to take care of the imbalanced data sets because it's have like very high imbalance in this case. That is one of our problem. And also we try to do both, like we try to increase the number of the minority events and also try to reduce the number of the majority events as well. But as I said before, we want to use bigger data set, not just only for 4 days. Right now, actually, the data that we collect from the InfoLogger, actually we have like about 3 terabytes, but for the computing resources that we have is not enough to handle all of this data. So that's why we need to get only the example set of the data in order to prove of the concept that we can do it. Yeah, at this time.
Okay, thank you.
Thank you very much.
Thank you, Dr. Monsak. Okay. Thank you very much, Dr. Pon, for your excellent presentation.
Thank you very much.